Our next speaker is Auroop Ganguly, who is a professor of civil and environmental engineering from Northeastern University. He's also a joint chief scientist at Pacific Northwest National Laboratory.
Thank you so much, Michael. Can you see my screen?
Not yet. Oh, here we are. Yep.
All right. So, so I'm going to take a very different track here relative to the other talks. But I'm going to take off a little bit right from where I think Nathan talked about turbulence is going to be with us for the next 100 years. And both George and Nathan talked about videotaping physics. So I'm going to talk about a problem. I'm going to talk about floods in the context of climate change and urbanization, building resilience to floods. Where are we in terms of some of these critical challenges that face society? What are the opportunities for KGML, broadly that umbrella? And maybe also, why is it that despite all the exuberance, and I'm not saying it's irrational, but all the exuberance around machine learning as applied to this specific domain, why aren't we seeing yet this area dominating, for example, the latest IPCC reports? What is still not happening? Hopefully, I'll not talk explicitly about that, but hopefully that'll come across. So the idea here is to talk about an end-to-end application in the context of flood risk management, given we are talking about climate change, given we are talking about urbanization. This framework, by the way, comes from the IPCC, and this talks about all the way from climate, natural variability in climate to anthropogenic climate change, which talks about then weather and climate events, including weather climate extremes. And then vulnerability, for example, infrastructures vulnerability and exposure, such as societal exposure. And across these different time scales from seasonal, sub-seasonal, interannual, decadal, even century scales, what is it that can be done? And what is it that broadly this umbrella term KGML that Vipin talks about, where and how can they help? So I'll try and illustrate that, this end-to-end story. This will be a bit of a whirlwind tour, if you will, rather than going into specifics, but I do have some citations scattered here and I'll be happy to discuss. But I do want to illustrate these through 4 questions, starting from the left side here. First question is, what can we do in terms of better understanding of hydrological and weather extremes from climate model simulations and observations? What can we, the second question is, given the understanding that we have and whatever we can do to improve, what can we do in terms of better translation to infrastructural or planning, design curves, operation curves, so information that relates to design of infrastructures and planning and operations as well. So then, so this sort of on the left side, these 2 questions relate to timescales, potentially interannual, but really mainly decadal to century scales. And then if we are thinking that, well, we are going to live under a situation of more intense, more drastic, at least in terms of impacts, more, exacerbating extremes, then we have to deal with risk management and adaptation. And there we are going to, I'm going to talk here about one aspect of risk management, which is sort of anticipatory or predictive analysis. So think of the first side of the curve if you're thinking hurricanes. And this here, I'm talking more about urban and watershed flooding. But if you were to think about hurricanes, the first part would be, okay, under climate change, what would happen to the intensity of the most intense hurricanes versus, well, if we are going to live in a situation where we will have more destructive hurricanes, let's say, then we need to improve our predictive skills, hurricane tracking systems, etc. So that's the context of the third question here, which then talks about short-term prediction of precipitation and hydrology. And then part 4 talks about, okay, what does this all mean in terms of climate adaptation? So we are going to look at one sector. We're going to look at transportation sector at regional and urban scales and try to see what all this means for resilience of this sector. And given this workshop is KGML, and particularly this session is machine learning, so hopefully this fits in. Where can some of these approaches, or what kind of approaches are being used right now, which could broadly fall under this umbrella of knowledge-guided machine learning, which is the theme of this workshop. And we need to understand that first, and then hopefully try to come up with better approaches to be able to solve these. Some of these solutions are needed now. And again, to go back to some of the previous speakers, yes, turbulence to solve turbulence, maybe it'll take 100 years or more, like one of the speakers was saying. But for some of these problems, we cannot wait that long. What is it that we can do in the interim? So if we think about floods, these are just some media articles, recent media articles, some just last month, a few days ago, some a bit older. And there's one article in Science. This is a news article, so I'm sort of lumping all of that. These are developed nations. This is Western Europe, this is US, this is Singapore, this is Japan. And even there, people are using this, people are using this term stunned. Apparently, scientists are stunned that we are having these kind of flooding. And this word comes from a Science report, news article. European deadly floods leave scientists stunned. So what is going on here? What can we do? Should we be in this state? And we are here, I'm more talking about, as I was saying, watershed and urban scale flooding. By the way, there was this Nature paper, which was published just a few days back. And what they talk about is floods are not only getting worse, but from satellite mapping, they have found that 10 times more people might be exposed to floods compared to what we thought previously. The change drivers being urbanization, mitigation infrastructure, flood mitigation infrastructure, levees, dams, etc., and human settlement in floodplains. The uncertainties continue to be things like population and climate, but also even records of floods and our ability to infer urban floods from remote sensing data. Now, when we talk about infrastructural lifelines in the context of floods, and when we talk about these floods in general, we talk about the climate context, we talk about understanding these extremes, we talk about the water system, for example, in watersheds in specific urban areas. We talk about infrastructures that are protective, such as storm drainage systems, levees, dams, nature-inspired systems. And then I'm inferring some of these from remotely sensed data from models, and then going into infrastructure resilience, for example, in the realm of lifeline systems, such as water distribution systems, communication systems, power grid, wastewater systems, and transportation systems. So there are these infrastructures which are sort of protective, and there are these infrastructure lifelines which are essential for human lives and sustainability. Now, in the context of floods, this was, by the way, a 2014 article that we wrote collectively with Vipin and his group and many others, such as Don Webels, etc. In the realm of, this is just a motivational article as to why physics-guided data mining is needed. And remember, this was 2014. But one thing there is that when you talk about floods and heavy rain, they have significant uncertainty. They occur more often than many of the other extremes. And they are among the ones that cause significant damage, including death. So it's important. On the other hand, models have limitations and various kinds of limitations currently in the physics and in terms of predictability. So the first set of limitation in terms of physics is models often progress slowly. So the last time there was some significant change in stakeholder relevant insights based on these models was, I would say, and this is a broad generalization, so I'm sure some folks will shoot me down for it, but was probably in the IPCC AR4 timeframe, which was the CIMIP3 suite of models. When IPCC AR4 was able to make the claim that yes, there is global warming, and yes, a lot of it is being caused by human emissions, and which got them the Nobel Peace Prize, et cetera, but that was then. So IPCC used CMIP3 and going from there to AR5, when we compared CMIP5 models, and it takes 7 years, remember. So CMIP5 was the last generation of models. The latest IPCC report, which some of you may have seen in newspapers, that used CMIP6, mostly used CMIP6, I would say. But anyway, so when we compared these models across generations with observations and with each other, in terms of stakeholder relevant insights or stakeholder relevant scales, it's not that they improved significantly, unfortunately. And this was 7 years later. And this happens sometimes. I mean, models stabilize for a while, then they improve and so on. But this is the state. And the other side of the story is that we are finding more and more that there is significant natural variability in this model. And some of this relates to what we know as chaos theory. Some of this may relate to other things, but the way its natural variability with large ensemble runs are characterized now, it does relate to extreme sensitivity to initial conditions. And just based on those routes, what we see, especially at the scales that we care about, such as urban scales, there is a lot of variability. This initial condition or natural variability, intrinsic variability, if you will, which then reflects itself in some way as projections, projection uncertainty. And this is potentially a limit to predictability, which we don't expect to significantly improve. So with all that, where are we in terms of understanding extremes? Well, if you think of water cycle within Earth system models, and this comes from a white paper that we submitted in response to a solicitation by Earth System Modeling Group at DOE, Department of Energy. So we're talking about the different kinds of challenges that still exist. There are many challenges, so I'll just highlight a couple of them. One is the natural variability in climate, which comes from climate oscillators, things like El Nino, things like Pacific Decadal Oscillation, and their impacts on regional land climate, so through what are sometimes called teleconnections. And then the other area is, how to translate or how to develop models so that the outputs are useful in terms of information that's needed for adaptation and impacts, and at scales that they are needed. And one thing that has been happening a lot, at least in terms of investment, is still early in that area, is within the structure, more or less within the structure of climate models, a lot of machine learning approaches are being built. I would call these broadly machine learning enhanced physics, where they talk about improvement in parameterizations. Parameterizations, by the way, are often physically based, but they are not first principles based physics. But trying to improve those parameterizations, the competition there, again, at a very broad general level, competition there would be with standard data assimilation approaches that have been used by the weather and the climate community. But broadly speaking, this area of KGML, knowledge-guided machine learning, where we talk about looking at huge data sets from model simulations, from remote sensors, and also from in situ sensors as they exist, and trying to extract insights from them and trying to extract insights related to extremes, in this case, related to uncertainties, but also maybe extracting insights which are causal and feeding back into the models. But in addition to feeding back into the models, overall helping us in our understanding of the science and using that understanding to get better information for impacts and adaptation. That's where I think knowledge-guided machine learning could fit in very well. So I'll just run through a few examples, and I have some citations here. I'll not cover them in any detail. But one area is in terms of teleconnections and in terms of understanding these oscillations, things like graphical methods, information theory, and recently even some deep learning applications are showing some promise or have shown some promise. And then in terms of relating across scales, things like deep learning, Bayesian deep learning, etc., are showing some promise also. And remembering that we have to think about uncertainty. I'd be terrified of designing anything or translating to design curves based on a single point prediction. We need uncertainties with our projections. So some initial promise, a lot of what I've seen is there's a lot of excitement and exuberance when we have these kind of things, but it's still some time before these are actually used in real world situations, either for discovery or to inform impacts and adaptation. So from there, from where we are in terms of climate science, in terms of understanding extremes and their uncertainties, getting towards design curves, there is a lot of work to be done. First of all, when we think about the American Society of Civil Engineers, they have been saying that our infrastructures remain poor. From D+, it has gone up to C- from 2017 to 2021, but still not grades anybody would be proud of. And especially for the kind of protective infrastructures, levees, dams, stormwater systems, urban stormwater systems, it still has not improved much. And all of us are aware of this with the new bill that's been passed. So we'll see what happens there, but a lot of work needs to be done here. In terms of translating, going from climate understanding to translating to design curves, it's almost tantalizing in that both over time, I mean, in terms of temporal and geographically, we do see that trend. We do see some trends. Some of these are significant when we talk about climate trends impacting design curves. But the uncertainties are large. And as I was saying earlier, we cannot ignore uncertainties in design and operations because then anytime, I mean, if we design with 1 point prediction with mean, then anytime that mean is exceeded, our designed bridges, dams, lifeline systems will fail. So, I mean, uncertainties are huge though in these cases. So again, this is some of our own work where you're also showing that, yes, that signal is clear at global scale and at, let's say, continental scale. But by the time we get to things like, I mean, regional scales, urban scales, those signals and those design curves, IDF, intensity, duration, frequency, or depth, duration, frequency curves, there's a lot of uncertainty. One thing that we did see, though, is that there could be creative ways to try and address those. So the same large ensemble runs run by scientists such as Clara Besser at NCAR, which are run for us to be able to understand the range of natural variability and hence plausible future scenarios. Those same runs may potentially be used as sources of data to estimate extreme values and for rare event analysis. I'll not go too much into that. But in terms, I mean here, but I have the citations there. In terms of uncertainty quantification, in addition to the typical ways in which we look at uncertainty from these models, which is looking at uncertainty based on comparing models with each other, and this can be in the past and in the future. And in the past, comparing models with observations. One other thing that we could do, and it's not something that's fundamentally new, of course, people have been doing this, but one thing we could do is we could use dependent structures that we extract from data, both from model simulated data as well as from observed data. And we can use physical consistency, especially some of the physics knowledge, if you will, that's not already embedded within models, and try to see if we can help, we can use those to constrain the uncertainty, not minimize, but constrain and understand and characterize the uncertainty. So here is one work that, that we did in that area based on Bayesian methods. By the way, if you happen to read this, please read the online supplementary information. That's where all the real stuff is. All right, so now we talked about understanding extremes in a climate context. I talked about translating to design curves, now getting to the other scale. If we are going to live in a world where these kind of things are going to happen more and more, then we need to have better disaster risk management and adaptation. And one part of disaster risk management is being able to do short-term prediction well. And in the case of urban floods and watershed floods, it predicts its quantitative precipitation forecasting at short-term and high resolutions. And again, as you can see from these media reports, the situation there needs to improve. And this is one area, by the way, I think Nathan and George are talking about, can we get videos of the physics? Here we can get videos of the physics. But again, here it does. There are intersections, of course, with things like turbulence and such, but we need practical solutions here. The operational model is HRRR. It comes from NOAA. And in that operational model, they do use model forecast. I mean, I would say in that operational approach, They do use different model forecasts. They use forecaster skills, and there's a lot of manual adjustment involved, which of course are often not scalable, may suffer from certain biases, but that's what we have right now. And theoretically, there has been some work in these areas. Theoretically, if you look at the top right, there is a theoretical bound which comes from chaos theory. And these forecast lead times on the x-axis in the top right, that sort of is going from, in this case, minutes to a few days. So if you look at theoretical bound, that comes from chaos theory, as I was saying, but then radar extrapolation or observation-based extrapolation have a lot of initial skill, which quickly decays for, within a few hours, but then these model skills pick up. There's some sort of complementarity. That's what people have suggested. Google AI recently came up with what they called a data-driven physics-free approach. Now, whenever I hear physics-free, especially from Google, it makes me think of Google flu. But it is it is true that within the context of, let's say, the first few hours, which is again also very important in terms of QPF, the physics that we know is not that much. So maybe these kind of things will improve. And we have done some work with hybrid physics and these kind of approaches, and looking at both physics from weather prediction models, observation-based extrapolation, mass balance, statistical methods, and even what would now be called shallow neural networks, together with what David McKay at some point used for what he called Bayesian methods. And recently we have tried some of these convolutional LSTMs also in this context. I have been trying to understand this whole Bayesian deep learning, just exploring and trying to understand where and how they work. Given sometimes people seem to even be able to predict random walk. So just trying to see how well they work and where they work in terms of these Bayesian deep learning, just polynomials with noise, but that's another story. Quickly, I can see Michael here, so I think my time is almost over, but quickly running through then the last part of the talk, which is one area of impact is transportation, lifelines, both at regional scales and at urban scales. And again, this is not something I'm making up. These are all news articles, recent news articles, which talks about how the climate change is impacting the world subways. This was New York Times. Boston's subway, this was Boston Globe. London Metro, this was BBC. And New York Metro, this was NPR. So all over the place, there are various network science and optimization methods that are being used to understand how cascading, cascading failures occur, understand robustness, and understand restoration strategies. We have been doing some of that, both for regional lifelines, such as the US Airport National Airspace System, as well as Indian Railways, trying to use network science and optimization method, both to understand cascading impacts and robustness, as well to understand recovery and restoration. We have looked at London, so we have looked at urban metros in the same way, and tried to compare our understanding with both network, so sort of what could be called complex network science kind of approaches, but also network optimization methods. So overall, I tried to do a sort of whirlwind tour in terms of risk assessment. We really need to get this going now in terms of comprehensive risk assessment, end to end, in one context maybe. So here I was highlighting that in the context of floods, and saying that we can ask questions across this realm of this IPCC formulated risk assessment framework, ask questions across these, and there are these different approaches, from graphical methods for teleconnections to physics-guided deep learning, for scale to extreme value analysis, and Bayesian, physics-informed Bayesian methods for uncertainty in one scale, and then going to hybrid physics and deep learning, and process-guided network science and optimization, all of which potentially could fall within this knowledge-guided machine learning umbrella. With that, thank you very much. Sorry, Michael, if I took a little bit over.
Okay, thank you. Let's ask this question. What is the impact of limited high-quality observations, only around 50 to 100 years, on our ability to predict extremes and potential role of kgml?
Yeah, so that's a great question. Significant impacts, of course. I mean, observations and model simulations dictate what we find. Models themselves are in various ways informed by observations. one thing that is happening, and this is a great question, over the last 50 years or so, we are getting a lot better with observations, a lot of remote sensing data and things like that. For example, the moment we start going back, we have to be creative about what kind of data sets exist. And especially when we go significantly back, of course, then we're only left with paleoclimate data and so on. But given the low frequency signals that often characterize natural variability of the Earth systems, observations, observed quality are incredibly important. And the idea is to be, well, we have to be as creative as possible. I mean, we might get more observations now. We might be able to, in some cases, substitute space for time. And there are some interesting work in those areas. We have to be creative. We can get paleo data, but we are just not going to get observations in the past. So we have what we have. What is the best we can do?
Great, great. I have a question. To what extent does the time frame affect the uncertainty? I mean, it's, you know, if you're predicting something a day out or 2 days out versus you're trying to predict whether there will be a dry year or a wet year. It seems like there's quite a difference there.
Of course. The uncertainty, of course, uncertainty is a function of the time horizon of prediction or projection, but also remember, we are not usually trying to predict or project the same thing. So when we are talking about understanding the statistics of extremes from climate or Earth system models and translating these to design curves, the first two part of the questions, or the first two questions are showing, we are talking about maybe interannual, but mostly decadal to century scale time frame, and we are talking about understanding statistics of the change, versus when you're talking about disaster risk management, quantitative precipitation forecast, and even to some extent what this means for the world's subway systems, we are talking about weather prediction scale. So what we are forecasting in the weather context or projecting in the climate context are not exactly the same.
Okay, thank you. We should go to our break now. We'll return at 3:10 Central Time. Thank you.
Thank you so much.